3I Atlas has already passed its closest point to Earth. It appeared, moved through our observational range, and continued on its path through the solar system. No alarms were triggered. No dramatic events unfolded in the sky. Yet something about this moment feels different from anything that came before. There was no spacecraft waiting in its path. No probe was sent to meet it. No material was collected. Everything we know comes from distant observation, from light measured across vast distances as the object moved on, indifferent to our presence. For decades, science has focused on understanding what these rare visitors are, their composition, their origin, their behavior. But as 3I Atlas moves away, another question begins to quietly take shape, one that is less about the object itself and more about us. This moment cannot be replayed. There is no rewind, no second chance to observe the same passage again. What remains is a growing sense that something important has just happened, even if we are not yet sure what it truly means. And that brings us to a question humanity has never had to ask so directly before. Can humanity chase an interstellar visitor like 3I Atlas, or is it already too late? Interstellar objects are valuable to science for a simple reason that is easy to overlook. They do not belong to our solar system. They were formed around other stars, inside environments shaped by different temperatures, different radiation fields, and different chemical histories than anything influenced by our Sun. Most objects we study in the solar system have been processed and reprocessed over billions of years. Solar radiation alters their surfaces. Gravitational interactions reshape their orbits. Even collisions slowly erase the original conditions under which they formed. Interstellar objects are different. They arrive carrying material that has never been recycled by our star, preserving information from a place we cannot visit directly. What makes them especially valuable is not just their chemistry, but the context behind it. Every molecule, every mineral signature reflects the conditions of a distant stellar system. These objects act like natural messengers, delivering physical evidence of how planetary building blocks form elsewhere in the galaxy. No telescope image, no simulation, and no laboratory experiment can fully reproduce that context. They are also extraordinarily rare. While countless bodies orbit our Sun, only a tiny number pass through from outside the solar system. Each one represents a unique combination of origin, trajectory, and history. There is no standard model for an interstellar visitor, because there is no such thing as a typical case. This is why size does not matter here. A small interstellar object can be far more scientifically important than a massive asteroid close to Earth. Its value lies in where it comes from, not how large or bright it appears. In a very real sense, these objects allow us to study other star systems without leaving home. And that raises a quiet but important question. If interstellar objects are this valuable as scientific messengers, have we ever truly encountered one up close? Or have we only ever watched them pass by from a distance? ʻOumuamua entered the scientific record quietly and unexpectedly. It was first detected only after it had already passed through the inner solar system and begun moving away from the Sun. At the moment of discovery, it was not announcing itself as something extraordinary. It was simply another fast-moving object. I've noticed because its motion did not match the familiar patterns of asteroids or comets bound to our star. As astronomers traced its trajectory backward, a remarkable picture emerged. ʻOumuamua was not orbiting the Sun at all. Its path was hyperbolic, a clear sign that it did not originate within the solar system. It had entered from interstellar space and would leave the same way, never to return. For the first time, humanity had confirmed the detection of a visitor from beyond the gravitational domain of the Sun. What followed was an intense effort to understand its physical nature using whatever data could be gathered in the limited time available. Its brightness varied in unusual ways. Its apparent shape appeared elongated. It showed no obvious coma like a typical comet. Yet its motion suggested subtle non-gravitational forces at work. Each observation added a new layer of intrigue, while also raising new questions. Because ʻOumuamua was already receding rapidly, observations were constrained by both distance and time. Telescopes around the world collected light across different wavelengths, but there was no opportunity for prolonged study. No spacecraft was positioned to approach it. No direct measurements of its surface or composition were possible. Everything scientists learned came from indirect signals encoded in light and motion. In the years that followed, these limited observations became the foundation for ongoing debate. Multiple models were proposed to explain its behavior. Some conventional, others more speculative. Each interpretation relied on the same small set of data, examined from different theoretical perspectives. The discussion did not end with a single conclusion, but instead expanded into a broader conversation about how little was known. Seen in hindsight, ʻOumuamua did not just introduce a new class of object. It exposed the boundaries of our observational readiness. And as the first confirmed interstellar visitor in modern astronomy, it left behind a question that would linger long after it disappeared from view. If ʻOumuamua was only the beginning, what did science truly learn from that first encounter? And how would it shape the way we respond the next time something like this appears? Borisov arrived with a different kind of clarity, where ʻOumuamua appeared almost like a silent shape slipping through the data. Borisov behaved in a way astronomers immediately recognized. It looked and acted like a comet. As it traveled inward, it developed a coma and a tail, showing that sunlight was warming its surface and releasing gas and dust into space. That familiar activity made Borisov easier to study in one important sense. A comet's outgassing leaves fingerprints. The gases and dust reflect and emit light at specific wavelengths, allowing scientists to use spectroscopy to identify chemical species and infer physical conditions. With Borisov, telescopes had more to work with than a changing brightness curve. They could read the object's chemistry in the light it produced. Observations of Borisov delivered a stronger, clearer dataset than the one available for ʻOumuamua. Astronomers tracked its activity over time and measured its spectrum in detail, building a richer picture of what it was releasing and how it was responding to solar heating, even without touching it. The combination of imaging and spectroscopy offered something closer to a profile than a silhouette. and that profile carried an important message. Borisov did not look like a perfect match to the comets we know from our own solar system. Its composition and the balance of volatiles suggested an origin shaped by a different environment, a different stellar chemistry, a different history. It reinforced the idea that interstellar visitors are not just rare, but diverse. At the same time, the nature of the interaction remained unchanged. Borisov was still observed from afar. The measurements, though stronger, were still indirect. There was no close approach, no direct sampling, no instrument placed near the coma to measure particles in real time. What improved was the quality of observation, not the fundamental strategy. In a sense, Borisov represented a step forward in confidence. It showed that with better timing, better coordination, and better tools, we can extract more meaning from these fleeting visitors. And once that becomes possible, a new curiosity inevitably follows. If the second interstellar object gave us a clearer view simply because we were ready to observe it, what would it look like if we encountered the next one under even better conditions? 3I Atlas entered the scientific conversation under noticeably different conditions. Unlike earlier interstellar visitors, it was identified with more time available for observation. Its trajectory was mapped earlier, giving astronomers a clearer sense of where it came from and where it was headed while it was still within a useful observational range. By the time attention focused on 3I Atlas, the global observing network itself had evolved. More observatories were involved from the start, operating across different wavelengths and sharing data in near real time. Optical telescopes, infrared instruments, and other sensors contributed pieces to a broader picture rather than isolated snapshots. The object was no longer seen through a single narrow window, but through multiple layers of measurement. This wider coverage meant that scientists were not limited to tracking brightness alone. They could study changes over time, compare signals across wavelengths, and test models against a more complete set of observations. In technical terms, the data density was higher. In practical terms, there was simply more to work with than there had been before. The technological context had also improved. Detection algorithms were faster. Coordination between institutions was smoother. Lessons learned from ʻOumuamua and Borisov shaped how quickly the community mobilized and what questions were asked first. There was a sense that this time, the tools were sharper and the response more organized. With better tools came higher expectations. 3I Atlas was not just another rare object passing through. It was seen as an opportunity to apply everything astronomy had learned about interstellar visitors so far, to push observations further and test ideas that previously rested on thinner evidence. And yet, for all these differences, one aspect remained unchanged. There was still no spacecraft sent to meet it. No instrument positioned nearby. No physical interaction of any kind. The encounter unfolded entirely at a distance, just as before. Which leaves a question quietly hanging in the background. If the conditions really were better this time, what was it that still kept humanity from acting? The first barrier appears when the discussion shifts from observation to motion. Interstellar objects do not behave like the asteroids and comets that remain bound to the Sun. Their speeds are far higher, not because they are being pushed by anything unusual, but because they are simply passing through. They arrive with velocities inherited from another stellar system and leave without slowing down. Unlike planets or long-period comets, these objects are not confined by closed orbits. Their paths are hyperbolic, meaning they are never captured by the Sun's gravity. They enter the solar system, curve slightly as gravity redirects them, and then continue outward on trajectories that will never loop back. From a physical standpoint, they are visitors, not residents. This has immediate consequences for timing. By the time an interstellar object is detected and confirmed, it is often already moving away. The window for action is measured not in years, but in months or even weeks. Every delay increases the distance, and every increase in distance raises the energy required to close the gap. Spacecraft, however, do not accelerate instantly. They are constrained by propulsion systems that build speed gradually. Chemical rockets deliver a powerful initial push, but once that burn is complete, the spacecraft coasts. Achieving a large change in velocity after launch requires careful planning, additional maneuvers, and often years of travel time. This is why chasing an interstellar object is not as simple as launching a faster rocket. The problem is not just speed, but timing, trajectory, and energy. It is a question of how to match or exceed a moving target that is already ahead and accelerating away under its own inertia. At its core, this is a strict problem of orbital mechanics. The equations are unforgiving, and small differences in velocity translate into enormous differences in outcome over astronomical distances. Understanding whether this barrier can be overcome requires more than ambition. It requires rethinking how motion through the solar system is achieved in the first place. So if speed is the first obstacle that stands in the way, the question naturally becomes whether physics itself offers any pathways around it that we have not yet fully explored. The most instinctive response to a fast-moving object is to try to follow it directly. If something is ahead, the natural assumption is that the solution lies in going faster. In spaceflight, however, that intuition quickly runs into physical limits. Chemical propulsion provides a strong push at launch, but it carries a fixed amount of energy. Once the fuel is spent, the spacecraft cannot simply accelerate again at will. Every additional increase in speed demands exponentially more fuel, and that requirement rises sharply when the target is already moving away at interstellar velocities. A direct pursuit also forces the spacecraft into an inefficient trajectory. Chasing straight after an interstellar object means fighting against both distance and timing. If the launch window is missed by even a small margin, the energy needed to catch up grows rapidly. What looks like a short delay on Earth can translate into an impossible gap across millions of kilometers. Simulations of these scenarios reveal a consistent pattern. Straight-line pursuit consumes enormous amounts of energy while offering very little margin for correction. The spacecraft spends most of its effort trying to erase a head start that it never truly closes. The problem is not that motion is impossible. but that the chosen path works against the physics of orbital travel. This is why space navigation rarely follows intuition. Efficient trajectories are almost never straight. They curve, loop, and borrow energy from gravitational fields. They rely on precise timing rather than raw thrust. In this context, the goal is not to outrun the target, but to place the spacecraft on a path that intersects it under favorable conditions. Seen this way, the challenge of intercepting an interstellar object becomes less about building a faster rocket and more about designing a smarter route. The question shifts from speed to strategy, from power to precision, and once that shift happens, another possibility begins to emerge. If chasing straight ahead is not optimal, what alternative paths could physics allow instead? One of the first truly viable alternatives comes from a technique spaceflight has relied on for decades, even if it often feels counterintuitive. Instead of carrying all the energy needed to accelerate, a spacecraft can borrow it from the motion of a planet. This is the principle behind gravity assist, a maneuver that uses a planet's gravitational field to alter a spacecraft's speed and direction without expending fuel. The physics behind it is well understood. As a spacecraft swings past a moving planet, it exchanges momentum with that planet. From the spacecraft's perspective, it gains energy. From the planet's perspective, the loss is so small it is effectively unnoticeable. The key point is that no laws of physics are being bent. Energy is conserved. It is simply being redistributed in a clever way. This technique is not theoretical. It has been used repeatedly to send spacecraft far beyond what their engines alone could achieve. Missions to the outer planets, to comets, and even to interstellar space have relied on carefully timed planetary flybys to reach their targets. In each case, gravity assist made the difference between what was barely possible and what was clearly achievable. Applied to interstellar objects, the idea becomes especially compelling. Instead of chasing a visitor directly, a spacecraft could be placed on a trajectory that takes it past one or more massive planets. Each encounter would add speed, gradually reshaping the spacecraft's path until it is no longer simply following, but intercepting. The resulting velocity could exceed what any onboard propulsion system could provide on its own. However, this power comes with constraints. Gravity assist depends entirely on geometry and timing. Planets must be in the right positions at the right moments. Miss those alignments, and the opportunity disappears. Designing such a trajectory requires years of advanced planning and extremely precise calculations. Long before any specific target may even be known. Because of this, gravity assist is best seen as a framework rather than a solution by itself. It opens a door that would otherwise remain closed, showing that high velocities are not forbidden by physics. It does not guarantee success, but it establishes a foundation on which serious interception concepts can be built. And once that foundation is recognized, the next question naturally follows. How has this idea been organized into concrete strategies for chasing objects that do not belong to our solar system? Project Lyra emerged as a way to turn abstract discussion into a structured scientific proposal. Rather than asking how to catch an interstellar object immediately, it reframed the problem around what might be possible over much longer timescales. The central idea was not urgency, but persistence. In this framework, interception does not happen near Earth or even within the inner solar system. A spacecraft would be launched onto a carefully designed trajectory that unfolds over many years. Instead of racing after the object, it would gradually reshape its path through a sequence of planetary flybys. Each gravity assist adding energy and refining direction. This approach accepts a key reality of orbital mechanics. High relative speeds and unfavorable timing cannot be solved quickly, but they can sometimes be managed slowly. By chaining together gravitational assists from planets such as Jupiter or Saturn, a spacecraft can accumulate velocity far beyond what its engines could provide alone. Over time, that accumulated speed could place it on a path that intersects an interstellar visitor far from the Sun. The trade-off is scientific patience. Project Lyra does not promise rapid results. The encounter, if it happens, could occur many years after launch, possibly when the target is already deep in the outer reaches of the solar system. Data would arrive late by human standards, but it would arrive from a distance and context that no telescope could ever replicate. What makes Project Lyra significant is not a single trajectory or mission design, but the fact that it has been examined seriously. Its assumptions have been tested with simulations. Its constraints have been discussed openly in academic settings. It represents a shift from speculation to analysis. From wondering whether interception is imaginable to asking under what conditions it might be achievable. In this sense, Project Lyra marks a change in mindset. It suggests that chasing an interstellar object is not necessarily about speed, but about endurance and planning. And that raises a subtle question that sits beneath the equations. When the target continues moving onward without pause, is patience alone enough to eventually close the distance? Solar sails introduce a very different way of thinking about propulsion. Instead of carrying fuel and expelling mass, a spacecraft can use light itself as the driving force. Photons may have no mass, but they do carry momentum. When sunlight reflects off a large, lightweight sail, it produces a small push on its own. That push is gentle over time. It becomes meaningful. The strength of a solar sail is not in sudden acceleration, but in persistence. As long as the sail remains illuminated, the spacecraft continues to gain speed. There is no fuel to burn out and no engine to shut down. The acceleration is slow, but it never truly stops. Given enough time, this steady pressure can build velocities that would be impractical with chemical propulsion alone. This makes solar sails especially attractive for missions that can be planned far in advance. A spacecraft launched early and allowed to accelerate for years could reach speeds that position it well for distant encounters. In that context, the sail is less about chasing and more about preparation. Placing a spacecraft on a trajectory that becomes increasingly energetic long before a specific target is even identified. The concept is not purely theoretical. Small-scale solar sail missions have already demonstrated that controlled flight using light pressure is possible. These experiments have shown that sails can be deployed, oriented, and navigated in real space, confirming the basic physics behind the idea. What remains is scaling the concept to missions that demand much higher performance. At the same time, solar sails impose their own constraints. Their effectiveness depends heavily on distance from the sun, since light pressure weakens with increasing range. They also require early commitment. Once an interstellar object is detected late in its passage, a sail launched in response would have little time to build the necessary speed. For this reason, solar sails are best understood as part of a long-term strategy rather than a quick response. They expand the menu of options, showing that continuous acceleration without fuel is achievable. But they also highlight a recurring theme. Preparation matters. And when preparation is not enough, the search for even stronger methods inevitably follows. Laser sails push the idea of light-driven propulsion to its extreme. Instead of relying on sunlight alone, this concept replaces the gentle pressure of the sun with an intense, focused beam generated by powerful lasers. In theory, directing that energy onto an ultralight sail could accelerate a spacecraft far more rapidly than any conventional system. The physics is straightforward, even if the engineering is not. A strong laser beam transfers momentum to the sail, producing a continuous force. With enough power and precise control, that force could drive a probe to a significant fraction of the speed of light. At those velocities, the distances involved in chasing an interstellar object begin to shrink in a way that no chemical rocket could match. This potential has made laser sails one of the most ambitious ideas in modern space propulsion. On paper, they offer something that other methods cannot. The ability to reach extreme speeds within relatively short timescales for interstellar interception. That promise is hard to ignore. Yet the gap between theory and practice remains wide. No laser system of the required scale currently exists. Generating and maintaining the necessary power would demand an infrastructure far beyond today's space capabilities. The sail itself would need to survive intense radiation without tearing, warping, or vaporizing. Guidance would have to be precise over vast distances, with no room for error. Because of these challenges, laser sails are often discussed as long-term investments rather than near-term solutions. They represent a future where humanity commands energy on a scale that makes new kinds of missions possible. But that future requires breakthroughs not only in propulsion, but in material science, energy generation, and global coordination. For now, laser sails occupy the edge of what might one day be achievable. They stretch our imagination and redefine what speed could mean in space exploration. And when a concept sits that far ahead of existing technology, it naturally forces a more grounded question. If such tools are still beyond our reach, what strategies remain realistic with the capabilities we have today? The idea of a standby spacecraft represents a fundamental shift in how interception is approached. Instead of trying to react after an interstellar object has already been discovered, this strategy begins from the assumption that reaction time itself is the limiting factor. When detection comes late and the target is already moving fast, even the best propulsion concepts struggle to close the gap. A standby mission accepts that reality and works around it. The spacecraft is launched years in advance and placed on a flexible trajectory, not aimed at any specific object. Its purpose is not to chase something known, but to be positioned where it can respond when something unexpected appears. In this model, readiness replaces urgency. Such a spacecraft would not carry a fixed destination. Its trajectory would be adjustable, designed to exploit gravity assists or gradual acceleration methods once a target is identified. When an interstellar object is detected, the mission would already be in motion, able to adapt rather than start from zero. The difference is subtle but profound. The response begins before the question is even asked. This approach transforms the relationship between discovery and action. Instead of astronomy leading and engineering scrambling to catch up, the two operate in parallel. Observation becomes a trigger rather than a starting gun. In that sense, the standby concept marks a move from passive observation to active preparedness. However, this strategy is not universal. A single spacecraft cannot cover every possible trajectory or timing scenario. Some objects would still pass too far away or too fast to intercept. Maintaining such missions also demands a long-term commitment, sustained funding, and tolerance for uncertainty. Years might pass without any suitable target at all. The standby concept does not promise guaranteed success. What it offers is a different posture toward the unknown. It acknowledges that rare events cannot be met with improvised solutions. They require patience, foresight, and acceptance of risk long before any payoff is visible. And that inevitably raises a practical concern. What is the true cost of staying ready for something that may not arrive on schedule? Pursuing an interstellar object comes with costs that extend far beyond engineering challenges. These missions are inherently expensive, demanding budgets measured in billions rather than millions. The hardware must survive for years, sometimes decades, while operating far from Earth with no possibility of repair. Every additional layer of flexibility, redundancy, and endurance adds to the price. Time is another major factor. Unlike missions with clear destinations and timelines, an interception effort may stretch across long periods with no guarantee of a timely encounter. Development alone can take many years, followed by extended cruise phases that test institutional patience as much as technical reliability. Results, if they come, arrive slowly. Risk is woven into every stage. A slight miscalculation in trajectory, an unexpected system failure, or a missed gravitational alignment could render the mission ineffective. Unlike orbiters or landers sent to known targets, an interstellar interception has fewer opportunities for correction. The margin for error is thin, and the consequences of failure are absolute. There is also no obvious commercial incentive to offset these risks. Such missions do not mine resources, establish infrastructure, or return products of immediate economic value. Their purpose is knowledge. They exist to answer foundational questions about how planetary systems form and how common certain materials and processes are across the galaxy. That focus on basic science requires long-term commitment. Governments and institutions must be willing to invest across political cycles. Leadership changes and shifting priorities. Not every nation can or will choose to shoulder that burden. For many, the scale of investment places these missions outside practical reach. As the discussion moves from possibility to responsibility, the challenge becomes less about physics and more about choice. Intercepting an interstellar object may be achievable in principle, but it demands resources, patience, and tolerance for uncertainty that few actors possess, which leads to a deeper consideration. In a world of competing priorities, who is prepared to bear the cost of reaching for knowledge that offers no immediate return? Large space agencies operate under constraints that go well beyond scientific curiosity. Their mission portfolios are shaped by the need to deliver reliable results within predictable timeframes. Projects with clear objectives, well-understood risks, and measurable outcomes naturally rise to the top of the priority list. An interstellar interception mission, by contrast, sits at the opposite end of that spectrum. Budget structures play a major role. Funding cycles are typically short compared to the lifespan of deep space missions. Agencies must justify expenditures year by year, often to changing political leadership. A project that may not produce data for decades is difficult to defend when compared to missions that promise near-term discoveries or visible milestones. There is also pressure to demonstrate success. High-profile agencies are expected to deliver results that reinforce public trust and institutional credibility. A mission built around a rare and unpredictable target carries the possibility of long periods with nothing to show, followed by the risk of complete failure if conditions do not align. That kind of uncertainty is uncomfortable in an environment where accountability is closely watched. Reputation matters as well. A failed flagship mission can echo for years, shaping perceptions of competence and decision-making. For organizations whose identities are tied to precision and reliability, cautious selection of projects is not simply conservatism, but self-preservation. Legal and policy frameworks add another layer of hesitation. Interstellar interception raises questions about responsibility, coordination, and ownership that are not clearly addressed by existing space law. Who authorizes such missions? Who bears liability? And how international cooperation would be structured remain open issues rather than settled rules. At the same time, caution does not mean indifference. Discussions about interstellar missions have taken place within advisory panels, workshops, and long-term planning documents. The idea has not been dismissed. It has simply been placed in a category that demands exceptional justification. Seen from within these institutions, restraint has logic behind it. Resources are finite. Expectations are high. And uncertainty carries consequences. Yet, as scientific ambitions expand, a subtle tension emerges. At what point does careful judgment protect progress? And at what point does it begin to quietly hold it back? While major institutions move carefully, the scientific community itself has been shifting in quieter ways. Over recent years, the number of academic papers addressing interstellar objects has steadily increased. What began as isolated studies focused on unusual detections has expanded into broader discussions about population statistics, origins, and the possibility of direct exploration. Alongside this growth in research, the tone of the conversation has changed. Ideas that once lived on the margins are now framed with formal models, simulations, and feasibility analyses. Interstellar interception is no longer treated as a speculative curiosity, but as a problem that can be broken down into physics, engineering, and mission design. The language has become more precise. And with that precision has come legitimacy. Much of this momentum has been driven by younger researchers. Scientists early in their careers are often more willing to engage with long-term questions, even when immediate results are uncertain. For them, interstellar objects represent an open frontier rather than a risky distraction. They bring fresh perspectives, new computational tools, and fewer attachments to traditional mission templates. This shift is beginning to surface in professional gatherings. Workshops and conferences now include sessions devoted to interstellar visitors and the strategies for studying them. These discussions do not yet dominate the agenda, but their presence signals a growing acceptance that the topic deserves serious attention rather than casual dismissal. Despite this progress, interstellar interception has not yet become part of mainstream mission planning. It remains an emerging idea, competing with established priorities and proven concepts. What has changed is not its status, but its trajectory. It is moving closer to the center of scientific discourse. Even if it has not arrived there yet, the result is a subtle but important tension. Interest is rising. Tools are improving. And the intellectual groundwork is being laid. What remains unresolved is how to bridge the gap between conversation and commitment. At what point does a concept stop being discussed and start being built? If a spacecraft were ever to approach an interstellar object directly, the scientific return would extend far beyond what remote observation can offer. For the first time, researchers would be able to examine material that formed around another star, not through inference, but through measurement. Composition would no longer be deduced from reflected light alone. Instruments could analyze particles, ices, and minerals in situ, revealing details that spectroscopy can only hint at. Close proximity would also allow scientists to study surface structure in detail, texture, layering, fractures, and coatings tell a story about how an object formed and how it has evolved over time. These features carry information about temperature cycles, radiation exposure, and collisions experienced far from our Sun. Such data cannot be reconstructed reliably from brightness variations or distant imaging. Direct measurements would shed light on emission processes as well. Outgassing, dust release, and other forms of activity could be observed as they happen, rather than inferred after the fact. Sensors could track how material responds to solar heating and how that response differs from what is seen in familiar solar system bodies. This would clarify whether interstellar objects follow the same physical rules, or whether new mechanisms are at work. Perhaps most importantly, close study would enable meaningful comparison. By placing interstellar material side by side with asteroids and comets from our own system, scientists could test long-standing models of planetary formation. Similarities would suggest universal processes. Differences would point to local conditions shaping outcomes in ways not yet fully understood. The impact of such findings would not be short-lived. Data from a single close encounter could influence theories of star and planet formation for decades. It would refine simulations, recalibrate assumptions, and inform future missions aimed at understanding how common certain materials and structures are across the galaxy. All of this represents a powerful incentive. The potential to transform our understanding of planetary systems is real and profound. Yet, as the promise grows clearer, so does the weight of the decision it demands. When the rewards are this high, does the scale of insight truly justify the uncertainty and risk required to obtain it? Interstellar interception also raises questions that cannot be answered with equations alone. Even if technology allows a close encounter, scientists must decide how that encounter should unfold. There is a fundamental difference between observing an object from a distance and interacting with it directly. And that difference carries ethical weight. One concern is intervention versus observation. Approaching closely enough to collect data may alter the object itself. Thruster exhaust, heat, or physical contact could change surface conditions or disrupt fragile structures. In studying something rare and pristine, the act of investigation risks becoming an act of modification. There is also the question of contamination. Interstellar objects originate in environments entirely separate from our own. Introducing terrestrial materials, even unintentionally, could compromise the very signals scientists hope to study. Conversely, bringing foreign material into closer proximity with spacecraft raises questions about containment and responsibility. Even if no immediate hazard is expected, scientific responsibility extends beyond a single mission. The first decision sets a precedent. How humanity chooses to approach its first interstellar visitor will shape expectations for future encounters. A cautious approach might slow discovery but preserve integrity. An aggressive one could accelerate knowledge while narrowing future options. At present, there is no widely accepted ethical framework for this kind of exploration. Space law and planetary protection guidelines were developed with planets and moons in mind, not objects that wander between stars. As a result, scientists are left to define boundaries for themselves, balancing curiosity against restraint. This makes interstellar exploration more than a technical challenge. It becomes a reflection of how science governs its own ambitions. Progress has always required pushing limits, but it has also depended on knowing when not to cross them. And that leaves a question that sits uncomfortably alongside the excitement of discovery. Even if we have the ability to reach out and touch a visitor from another star, should we choose to do so at all? 3. iAtlas is no longer just another data point in an expanding catalogue. It has begun to take on a different meaning within the scientific conversation. Beyond its measurements and models, it represents a moment of awareness. A point where observation turned inward and forced a broader reflection on readiness. What this encounter quietly exposed was not a lack of knowledge, but a mismatch between capability and coordination. Many of the necessary technologies already exist in some form. Detection systems are improving. Trajectory modeling is precise. Propulsion concepts have been studied in detail. Yet, when the object appeared, these elements did not converge into action. They remained separate, not quite aligned in time or intent. The experience highlighted how slowly processes move compared to the phenomena they are meant to address. Interstellar objects do not announce themselves decades in advance. They arrive, pass through, and depart on timescales that challenge institutional rhythms, planning cycles, approval chains, and mission development simply operate on a different clock. As a result, 3. iAtlas has come to symbolize a gap rather than a failure. A gap between what science understands in principle and what it can execute in practice. Recognizing that gap is itself a form of progress. It shifts the discussion from individual missions to systemic preparedness. From reacting to events to anticipating them. This realization has begun to influence how future encounters are framed. The emphasis is moving toward readiness, flexibility, and long-term positioning rather than last-minute response. 3. iAtlas did not force an immediate change, but it clarified what needs to change if the next opportunity is to look different. In that sense, the object marks a turning point in perception, not because it demanded action, but because it revealed the cost of hesitation in a universe that does not wait. And that leaves a lingering uncertainty at the heart of the moment. Did this realization arrive early enough to reshape what comes next? Or has it emerged only after the opportunity has already slipped beyond reach? Predicting when the first true interception mission might occur requires balancing realism with possibility. It is unlikely to happen within the next few years. The technical groundwork, institutional alignment, and long-term planning such a mission demands cannot be assembled overnight. Even the most optimistic scenarios require time to mature. At the same time, this is no longer a question pushed into a distant century. The underlying physics is understood. The concepts have been modeled. Pieces of the necessary technology already exist in partial form. What remains is not a breakthrough discovery, but a series of choices about priorities, funding, and coordination. The timeline depends heavily on decisions made now. Investment in detection systems determines how early future interstellar objects are identified. Investment in propulsion research shapes how quickly spacecraft can respond. Investment in mission architecture defines whether readiness becomes a standing capability or remains an abstract idea. Strategic vision plays an equally important role. Agencies and governments must decide whether rare, high-risk opportunities justify long-term commitment. These are not decisions driven by urgency in the moment, but by how much value is placed on preparedness for events that cannot be scheduled. every delay carries a quiet cost. Interstellar objects will continue to pass through the solar system regardless of human readiness. Each one represents a fleeting alignment of chance and opportunity. If the systems needed to act are not already in motion, that alignment dissolves without consequence. Except for what might have been learned. Time, in this context, is not neutral. It moves forward whether plans are in place or not. The question is not simply when the first interception could happen, but how many opportunities will pass before readiness catches up. If action is postponed too long, how many visitors will slip through before the first pursuit ever begins? The journey through this question leads to a conclusion that resists simplicity. In principle, humanity can chase an interstellar visitor. Physics does not forbid it. Technology points toward pathways that make interception conceivable. The idea itself no longer belongs to speculation alone. But possibility does not always align with timing. Not every visitor can be reached. Not every encounter allows preparation. Some objects arrive and depart on timescales that leave no room for response. No matter how advanced our tools become, in those cases, what passes by also takes something with it. Information that cannot be recovered. Context that can never be reconstructed. The universe does not pause while we decide. It does not wait for budgets, approvals, or consensus. Interstellar objects move on their own schedules, shaped by forces far beyond our influence. Each one carries a fragment of a larger story, and once it is gone, that fragment is gone with it. What remains within our control is not the motion of these visitors, but our readiness to meet them. Preparedness is a choice. It reflects how seriously we take the unknown and how much we are willing to invest in understanding it before it appears. The future of interstellar exploration will be defined less by any single mission than by the decisions made long before the next object is detected. In the end, the question does not belong to technology or even to science alone. It belongs to intention. When the next visitor enters our solar system, the outcome will depend on whether we chose to be ready or chose to wait. And that brings us back to the question that now hangs over everything we have discussed. Can humanity chase an interstellar visitor like 3i Atlas, or is it already too late?